Okay, we are live. And it really is we, because I have a dog with me. I am Doug. This is my beautiful assistant Mocha, whose job right now is to hide which soccer jersey I'm wearing from you. So I'll move her out of the way. Yeah, this is Barcelona. And it's cold October-y, so I may as well be inside thinking about math, which will heat up my brain and then make the rest of me feel warm. Now, my beautiful assistant is going to actually help this time, but as soon as she helps out a little bit, I'm going to send her upstairs. What I've done is I have prepared this page. Let's see if I can get the camera to see it properly. There you go. With all the digits from 1 to 9 on it. And I also have a whole bunch of these little dog treats. So what I'm doing is I'm putting one dog treat on each of the numbers. And I am going to put this on the floor, and you won't be able to see it. You'll just have to take my word for it that I'm telling you what's happening. And the dog will be allowed to take the treats. And the way she's going to help is I need 3 digits, 2 to make an improper fraction for today's lesson, and 3 to make a mixed number. So I need 5 digits. I'm going to choose the first 5 digits that she chooses a dog treat from. Let's do that right now because I know the dog really can't wait. She's really trembling in anticipation. Okay, so here's the pile of dog treats. See, they're all spread out on the page. I have to put this down. I'm not even on camera anymore, am I? And then I put the dog down. Oh, okay. So now I'm going to put the dog down, and I have to be very careful to notice which ones she gets first. Okay, that's the 7, 2, 7, 9, 4, 5, 8. 7, 9, 4, 5, 8. 7, 9, 4, 5, 8. Where's my chalk? Where's my chalk? Here's my chalk. 7, 9, 4, 5, 8. There. Ow. Now it's time for the dog to go upstairs so that she doesn't disturb us. All of those treats are gone. You must realize they're gone now. She's walking around saying, where did all the treats go? Okay, hang on. Watch the chalkboard wall just for a second. Mocha, come on. Come on. Come on. Over here. Go. There's a whole bunch more treats upstairs. Go. Okay. And now we can get into our lesson. So this lesson this week is all about improper fractions and mixed numbers and being able to convert back and forth between those two forms of a number. I am using this little model that a mixed number has 3 values in it. There's the whole number, which is the big one. Then there's the numerator and the denominator. We know about numerators and denominators and fractions. And then an improper fraction has a numerator and a denominator, but the numerator is bigger than the denominator if it's an improper fraction. So we're going to take the digits that Mocha chose, and we're going to assemble them into an example of a mixed number and an improper fraction. Okay, 7, 9. I'm not going to put the 7 over the 9 because that would not be an improper fraction. So what I'll do is I'll put the 9 over the 7. There. And 4, 5, 8. That's good. I can just make the 4 the whole number, the 5 the numerator, and the 8 the denominator. See, dogs are good at math. Okay, now we're going to convert this into an improper fraction, and we're going to convert this into a mixed number. And we'll do that later on in the lesson. First, I'm going to talk about how we do that. So my mixed number example chosen by Mocha, I'm going to move it over here. And we'll use it later. And this improper fraction I'll put over here. Will it fit? And yes, that does fit. We're ready to go. Thanks to the dog, we have a math lesson. Let me move this clipboard out of the way. And of course, I need my fizzy water, so I'll open my can of fizzy water now because all of that excitement made me thirsty. Okay, that's mandarin flavored fizzy water. A delicious, sparkling, 0-calorie treat for a math teacher. I'm going to erase some of this stuff that is not necessary. So I'll leave the phrases improper fraction and mixed number in their places because they probably won't get in the way. If they get in the way later, I'll erase them later. So, where is my list of examples? I have a pile of examples here. I'm going to take it, I only have 2 pages because really I needed a bunch of fractions to transform it from one form into the other. So I am starting with converting an improper fraction into a mixed number. So an example with some numbers that are not too crazy big to start with, 13 halves. Now there's a trick that I like to teach for doing this. I know that this is really a division, and we can show it with a division, and I'll do that later on with at least one example. I know that's a really good way to explain how we're turning an improper fraction into a mixed number. But my trick that I like to do is I like to take the numerator, and I imagine that's 13 people. Let's say 13 people in a physical education class who are about to play some sort of game. So I need 13 people. Now I'm not going to draw detailed people. What I'll do is just put little circles to represent the 13 people. And in a gymnasium, these people are spread around in the room. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay, so there's the 13 phys ed students. The phys ed teacher walks into the room and says, I need you to break into teams of 2. I need groups of 2. So what happens? The people form a group. They either form a group with someone who happens to be standing right next to them, or they go and they find their friend and they form a group with the friend. But one way or another, all of these groups of 2 get formed because we're playing some sort of game where we need teams of 2. So what happens, we form all of the teams of 2 that we can, and sometimes there's going to be some left over. So what is this person who's left over? They're the remainder. In math, they're the remainder. So how do I convert an improper fraction to a mixed number with this cute little trick? I want the mixed number to have the big number and the numerator and the denominator. Well, the big number is going to be how many groups of 2 I managed to form. 1, 2, 3, 4, 5, 6. We made 6 groups of 2. And then the numerator is going to be the remainder. There was 1 left over, that's my remainder. And the denominator is going to be the same denominator that we started with. So 6.5 is the mixed number version of the same number that we express as 13 halves when it's expressed as an improper fraction. So improper fraction, the numerator is bigger than the denominator, and there is no whole number next to it. A mixed number, there is a whole number next to it, and usually the numerator will be smaller than the denominator. And this is a way of simplifying a fraction. Improper fractions are really good to work with, but final answers sometimes should be expressed in their most simplified form, and a lot of people will say this is more simplified than that. So you need to be able to do it. And we want to be able to do this in either direction. Sometimes we have a mixed number and we want it to be improper fractions, so in that case we would prefer 13 halves. But sometimes we want the mixed number. We consider it more simplified. We would prefer 6.5. They're the same number. 13 halves and 6.5 are the same number. So that's an example of how to do this, and it works quite well so long as the numbers aren't too big. So let's do a few more examples where the numbers are not too big, and we'll use this strategy. I'll erase this example. And what's my next example? How about 22/3? Okay, I'm going to put little X's for the students in the physical education class this time. I need 22 of them, so I'll put 22. That's 15, 16, 17, 18, 19, 20, 21, 22. There, I have 22 students in the physical education class. The phys ed teacher walks in and says, I need teams of 3. This time it's teams of 3. So people form teams of 3 with the people close to them or with their friends. And let's make several teams of 3. Let's see how many teams of 3 we will make. This is working very well. It's fun. It's easy to do. The remainder is 1 again. It doesn't have to be 1, but this time it's 1. The last time it was 1. It doesn't matter. I just have to make teams of 3 until I can't anymore. And then I need to count them. 1, 2, 3, 4, 5. There are 7 teams of 3. and the remainder, there is 1 left over. And the denominator is the same as the one we started with. So 7 1/3 is the mixed number version of 22/3. That is a cute trick. I like it, but it does get a little bit long drawing all of these x's and all of these teams. So when you get some larger numbers, it will start to become inconvenient. Let's do a third one, though. Let's do a couple more using this strategy, and then we'll move on to a strategy where we don't draw a physical education class. How about 15/4? Okay, this one won't be so bad because there's only 15 students in this phys ed class. I'll use little triangles to represent the students. So 5, 6, 7, 8, 9, 10, 11, 12. It does get a little long. 13, 14, 15. Okay, 15, want to double check. 5, 10, yep, 15. And this time we need teams of 4. Okay, so let's make teams of 4. There's 1, there's 1, here's 1. That one kind of looks like a face. And the remainder is 3 this time. We got 3 teams of 4. So my whole number is 3. The remainder is 3, that's my numerator, and the denominator will be the same. 3 3/4 is equal to 15/4. They're really the same number. This trick always works. One more done this way. How about 23/5? 23/5. Okay, it's 23. I think I'm going to go back to doing little circles. They're faster to draw. I need 23 of them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. That doesn't look good. 15, 16, 17, 18, 19, 20, 21, 22, 23. Let's fix that one, and we'll fix that one up a little bit. Okay, 23, double check. 3, 7, 12, 14, 16, 18, 23. Yep, and we need teams of 5. So I need to break this up into groups of 5. And there's all sorts of different patterns we can draw while we do this. Here's a nice long snaky one. Okay, remainder 3. Okay, so how many groups of 5 did we get? We got 4 groups of 5. The remainder is 3, that's my numerator. The denominator is the same, it's going to be a 5. 4 3/5 is equal to 23/5. It works, it always works. I'll put my 5th example up. 41/8. 41/8. Okay, I finally reached that point where I don't want to draw all of those students in the phys ed class anymore. 41, draw 41 of them. So this is what happens to students as well when they like using this trick to convert an improper fraction into a mixed number. That once the numerator especially gets really large, it starts to take a little long to do. So you want to find another way of doing it. And of course there is another way of doing it. There's more than one other way of doing it. The way I usually do it is just in my head. I'm saying, well, how many times does 8 fit into 41? So it's kind of like a division problem backwards. 8 times 5 is 40, I say to myself, and that's almost 41. 8 times 6 would be 48, and that's too big. It's more than 41. It's not going to work. So 8 times 5 equals 40, so therefore my whole number, my big number, is going to be 5. And then if I have 8 times 5 and I get 40, what's my remainder? 41 minus 40 is equal to 1. My remainder is 1. The denominator stays the same. It's really the same trick. I'm just doing it without drawing a phys ed class. All right, so that works, and you don't have to draw 41 dots to do it. So as the numerators get larger, this approach can be preferable to the student and even to the teacher. Okay, let's do a bunch more where we have some larger numbers where we don't want to draw a physical education class, and just to get a bit more practice. The good thing about this type of math lesson is you can get through an example quite quickly, so that means you have time to do a lot more examples. And a lot more examples is never a bad idea in math. I'm checking the time. It has been almost 15 minutes, almost a quarter of the planned amount of time for this lesson. I made 40 examples. So in 15 minutes, I should have done about 10 of them. Let's see how many I did. 1, 2, 3, 4, 5. Okay. And we haven't even gotten to the mocha chosen examples yet. But I think they'll go a little bit faster now because I'm not drawing all of these phys ed classes. Okay, so how about 32/9? How many times does 9 fit into 32? Now, if it takes a little bit of time to figure that out, that's fine. If you need to start writing things down to figure it out, that's fine. Do what you have to do. But if in your head you're able to say, I can remember my multiplication tables, and I remember that row next to 9, and that column below 9, and it's counting up by 9s, that row and that column, 9, 18, 27, 36. So what I'm doing is I'm counting up by 9s until I get to a number that's bigger than this numerator. 9, 18, 27, it's not bigger than 32 yet, but 36 is bigger than 32. So I go back one, and it's 27 that I need. How do I get 27 from 9? I multiply it by 3. So 9 times 3 equals 27. That means the big number I need is the 3. And 9 times 3 equals 27. The next thing I do is I subtract. 32 minus 27 is 5. That's going to be my remainder. And then the denominator stays the same. Kind of like a nice sliding downhill as you do this question, because it always ends with keeping the same denominator that you always had, which is not very confusing. So that's good. And 32/9 is equal to 3 5/9. It's the same number, really. It's just a different way of expressing it. This is more useful if you're in the middle of a problem where you want to multiply fractions or something. This can be a little bit awkward to work with when you're multiplying fractions. I really like improper fractions because they are useful to me when I'm partway through a long process. But a mixed number is a more simplified and a neater, tidier version of the number, which makes it good as a final answer. Okay, 32/9 is equal to 3 5/9. Let's do a few more pretty quickly. I'll talk my way through it, but what I'm really doing is I'm using the knowledge that I developed when I became familiar with multiplication tables. And that knowledge is so useful. You use it again and again for so many different things, and this is just one of them. 25/12. How many times does 12 fit into 25? It fits into 25 2 times. 2 full 12s will fit into 25. 2 times 12 is 24. The remainder, therefore, is 1. 25 minus that 24 is equal to 1. That's my numerator. The denominator is the same. Yes, this does go rather quickly. And in fact, I don't need as much chalkboard wall space, so I can do the next example without erasing this one. How about 25/9? Here, I'm using 25 as my numerator again, but it's a different question because the denominator is different. How many times does 9 fit into 25? Only 2. Only 2 full 9s fit into 25. 9 times 2 is 18. 25 minus 18 is 7. My numerator is 7. My remainder is 7. And the denominator stays the same. 2 7/9 is equal to 25/9. It makes sense. It's fun. It's an example of one of those things that I want a whole book full of so that I can do them while I'm waiting in the doctor's office. Or wherever it is that I'm waiting around on a little board. A little book, a puzzle book full of improper fractions that I need to convert into mixed numbers. That's fine with me. How about, this one looks a little bit more challenging. Let me give myself a bit more chalk. I ran out of chalk. I have to reload the chalk thing. One day I'll find a use for all those little leftover pieces of chalk. Okay, 53/7. It's getting a little more challenging. But that happens with math, it happens with numbers, and does it stop us? No, because we have a technique that we have learned, and the technique works. The phys ed teacher technique would work here, but drawing 53 students, that would take a little bit of time. I think I'm going to switch back to I'm going to stay with the technique I've been using lately. How many times does 7 fit into 53? That might take a little longer. But again, it's the multiplication tables. The 7s in the multiplication table. 7 times 5 is 35. Nope, not big enough. 7 times 6 is 42. Not big enough. 7 times 7 is 49. 49 is almost as big as 53. Let's just check. 7 times 8 is 56. That's bigger. That's too big. It didn't work. 7 times 8 won't work. So it's 7 times 7. I will have 7 full groups of 7 that are in that class full of 53. Okay, 7 times 7 is 49. 53 minus 49 is 4. and my denominator stays the same. It's 7 4/7. That's kind of a cool looking number. I like that number. And I didn't know it was going to turn into 7 4/7 when I chose this as my example. I like it. It's fun. Let's do some more. 34/15. Okay, so 34, we're going back to numerators that are not so gigantic after all, but this denominator got a little bit bigger. Is that going to be a problem? No. How about the fact that 15 isn't one of the numbers in either the left column or the top row of a multiplication table? We go up to the 12 by 12 usually. If you don't go up to 15 by 15, do you know how to deal with 15s with multiplication? Yes, you do, because it would just be like counting up by 15s. 15, 30, 45 got too big. Okay, so 15 only fits into 34 twice. My big number is 2. 34 minus 30 is 4. My remainder is 4. My numerator is 4. The denominator is the same. This always works. This is fun. Okay, let's see what I did here. 34/15, I did that one. Okay, I have a couple more, and then we'll show a division, because I don't want to keep on pretending the division's not part of this. Let's face it, fractions look like the division symbols for a reason. A fraction is a division. Little pause for water. Okay, 33/10. Well, this looks like a fun one. Why does it look fun? Because it has a 10 in it. It has a nice round number with a 0 at the end. And it has 33. It has that double digit type of number. Those are always fun. How many times does 10 fit into 33? That's a quick one. 10 will fit 3 full times into 33. 10 times 3 is equal to 30. Then 33 minus 30 is equal to 3. So my remainder and my numerator is also a 3. And then the denominator, of course, is the same. It's just fun. How about 44/5? Here's another one where the numerator is a double-digit thing, and the denominator is a nice round number, that 5. Everyone loves 5. Okay, how many times does 5 fit into 44? Yes, I know that the students are saying the answer before I can even finish asking the question. 5 will fit into 44. 8 full times. 44 minus, wait, what is 5 times 8? It's 40. 44 minus 40 is equal to 4. That's my remainder and my numerator. And the denominator is the same. It works. It always works. It's fun. How about, here's one. I'm getting a little bit more daring with the size of these numbers, just to prove to the students that we don't have to be afraid of bigger numbers. When we learn how to do something with the smaller numbers, then the technique still works with the bigger numbers. So let's do one, and this time I'm going to show the division. It's not a very long division. How about 83/12? Okay, so I'm dividing 83 by 12. And I can show that as a division. There's my 83. There's my 12. I asked myself, can 12 fit into 8? I just used the first number at first. Can 12 fit into 8? No. So I have to go over here and I have to write an answer one digit further over. I'll write an answer there. Can 12 fit into 83? Yes, 12 can definitely fit into 83. 12 is smaller than 83. How many times does 12 fit into 83? Well, knowing my multiplication tables, I know that 7 times 12 is 84. So that means it didn't fit into 83. So I'd go back down from 7 to 6. 6 times 12, which of course I know from multiplication tables, is equal to 72. And then I am going to subtract. 83 minus 72 is 11. I have everything I need to know to answer my question, which is what mixed number does 83/12 turn into when we convert it? That's going to be my big number, the 6. This is my remainder, the 11, and the denominator, of course, stays the same. So when you think about it, what I just did isn't really very different from what I was just doing sort of in my head with the previous bunch of examples. But as the numbers get larger, you might have to slow down in order to figure out the numbers that you need to convert to a mixed number. If you have to slow down, you should slow down. Okay, and now I have a bunch more with some fun larger numbers in them to practice with. I'm not going to show all of these divisions. I'm going to go back to doing it with this logic and the remembering multiplication tables as my technique, and I'm going to look at the time. And with 1, 2, 3, 4, 5, 6, 7 more examples, and about 5 minutes, I think I might be able to do this. Of course, if I get to the halfway point of my lesson, and I haven't finished all of these examples, I just won't use all of them. It's better to have too many than not enough. Okay. '89ths. Need more chalk. 89ths. How many times does 9 fit into 80? Almost 9 times, because 9 times 9 is 81. So it's going to be 8 times. 8 times 9 is 72. 80 minus 72 is equal to 8. Denominator the same. It's working. Okay, how about 67/8? So larger numerators and even some kind of larger denominators just do not faze me. I know what I'm doing works. 8 times what is equal to 67? Well, 8 times 8 is equal to 64. And that's almost as big as 67. 8 times 9 is 72, and that's too big. It's bigger than 67. So 8 times 8 equals 64. That's what I need. My big number is going to be an 8. 67 minus 64 gives me a remainder of 3. Denominator is the same. It works. It always works. It's fun. It's that feeling of power when we know that we know how to do something. How about 37/5? This one's not so scary. It's almost small enough numbers to be drawing a physical education class, but I won't. How many times does 5 fit into 37? 5 times 7 is equal to 35. So 7 is my big number. 5 times 7 is 37 minus that 35 is equal to 2. That's my remainder, and my numerator, denominator the same. It works. How about 67/12? Okay. How many times does 12 fit into 67? 12 times 5 is 60. 12 times 6 would be 72, which would be too big. So it's 12 times 5. I'm using 5 as my big number. 12 times 5 is equal to 60, and 67 minus 60 is equal to 7. There's my remainder and my numerator, and 12 is my denominator. It works. It's fun. I have a couple more. Let me see what the time is saying. I'm going fine. I'm going to be able to use exactly all 20 of the examples that I put together. And then, of course, we'll have to do Mocha's. Mocha's is looking kind of simple, actually, now. This is looking like one of the easiest ones. But that's fine. We'll do Mocha's last. Okay, 67/12 we did. How about 76/15? Well, this is a bit of a crazy one. Again, we have 15, which is larger than the 12 and the 12 in the multiplication tables, but it's 15. It's kind of a round number. It's not that hard to work with. 76 is a little bit of a crazy numerator as well. How many times does 15 fit into 76? 15 times 5 is equal to 75. 76 minus 75 is equal to a remainder of 1, so my numerator is 1, denominator the same. Wow, cool looking number. Okay, how about 53? What is it with all these 15s? 53/15. 15, counting up by 15s, expressing it that way. 15, 30, 45, but then we get 60. 60 is too big. 15, 30, 45. That is 3 15s. That's my big number. 53 minus 45 is equal to 8. And the denominator is the same. It works. Okay, one last one. Oh, giant numerator. I'm a little scared. 120. Why am I walking over there? I have this in my hand. 127 is my numerator. 127 15ths. There I am with the 15 again. Wow. I have to slow down a bit. But 15 times 2 is equal to 30. 15 times 4 is equal to 60. 127 is just a little bigger than 2 times 60. So 15 times 4 is equal to 60. 15 times 8 is equal to 120. 127 minus 120 is equal to 7. Denominator stays the same. Crazy big numbers both on the top and on the bottom, and yet we can still do it. If you can't do it in your head, don't do it in your head. Do whatever you have to do. Write down some multiplications. Count up by 15s. That might be a really efficient way of doing it. Drawing 127 students in a phys ed class, I do not recommend that. That would take a while. But if it's what you have to do, if you're really determined to get the right answer, and you know that you will get the right answer with that technique, well, I guess I can't criticize it very much. Finally, we're going to do the very last example of this, which is Mocha's example, which seems painfully simple. But of course, she is a dog. She's not very good at math. She is very good at figuring out where dog treats are. Okay, how many times does 7 fit into 9, Mocha? Talking to you, Mocha, she's up there somewhere. Okay, 7 fits into 9 only once. So my big number is a 1. 7 times 1 is equal to 7. 9 minus 7 is equal to 2. My remainder on my numerator is 2. Denominator stays the same. We did Mocha's example. Okay, this is fun, but it's time to move on to something else. How am I doing for time? Really, really good. Okay, I'm going to erase this. Now we're going to start with mixed numbers, and we're going to convert them into improper fractions. Now, a lot of students will say, well, that's even easier, but we still have to practice it. So the other way around, how do I do this? There's a mixed number. Well, should I use Mocha's example? No, Mocha's example is too complicated. So Mocha's example of the other one was a little bit too easy. This is a little bit more of a complicated one. You never know what a dog's going to do when you get her involved in a math class. I'm going to start with a nice, simple-looking mixed number. 2 1/2. How do I convert this into an improper fraction? Well, there's a technique to doing it. The big number has to be multiplied by the denominator and then to the answer we add the numerator. So there's a plus numerator. Wow, this is long. Well, the words are long, and it's all fitting though. And that will give me my new numerator. New numerator. Seems complicated, eh? Seems quite long, except the next step is, it takes a while to write because of these giant long math words, denominator stays the same. Are we surprised? We're not surprised because we're so good now at converting an improper fraction into a mixed number, and every single time we found the denominator was staying the same. When we're doing the opposite, converting a mixed number to an improper fraction, we shouldn't be too surprised to find out that the denominator stays the same. So again, we're rolling downhill. Once we get through this first part of the exercise, then it becomes easy to finish it because the denominator remains the same. Okay, so I'm going to do it now. All of this, big number, that's a 2, times the denominator, which is another 2. 2 times 2, that gives me 4. But then I add the numerator, plus this 1 is my numerator, gives me my new numerator. Denominator stays the same. It was a 2, 5/2. Okay, now is this the best way of writing it? There's more than one way to write this. I'll write it differently when I do the next example. But we have to remember this. I'm going to erase it after a couple of examples, but we have to remember this is how it's done. Big times the denominator plus the numerator. That gives me my new numerator. New numerator, not easy to say, but kind of fun to say. New numerator. Denominator stays the same. Let's do another one. I'll show it slightly differently, how I showed the little calculations. So we started with 2 1/2, very straightforward example. My second one, I need more chalk. 4 1/4. Big number's a 4, and I'm multiplying it by the denominator, which is a 4. But then I'm adding the numerator, which is a 1. That is going to be my new numerator. I'm going to write it as a numerator, why not? Denominator stays the same. Well, simplifying this, 4 times 4 is equal to 16 plus 1 is equal to 17. 17 quarters is the improper fraction version of this number 4 1/4. It works. Okay, now I'm going to erase this, and we're going to practice this quite a few more times. We're still not dealing with numbers as challenging as the one that Mocha chose, so we'll wait a little bit before we use hers. Remember, when I'm erasing, big number, that's the whole number, times the denominator, plus the numerator, gives me my new numerator. Denominator remains the same. How about 7 1/3? Big number, 7, times denominator, 3, plus numerator, 1. Denominator stays the same. 7 times 3 is equal to 21, plus 1 is equal to 22. 22/3 is the improper fraction version of 7 1/3. It worked. Didn't erase that part very well. Let's do another one. 5 3/4. Okay, all of my examples so far had a 1 as the numerator. But this doesn't. Do we need a 1 as the numerator to be able to do this? No. Big number, the whole number 5, times the denominator 4. 5 times 4, plus the numerator, that's plus 3, over, same denominator. 5 times 4 is equal to 20, plus 3 is 23. Denominator is same. 23/4, 23/4 is the improper fraction version of this number. It works, it's fun. Let's think about what we were doing before. We were doing this in the other direction before. Let's do it. 23/4. How many times does 4 fit into 23? We're not surprised to hear that it's 5. 5 4s fit into 23. And then if you do 5 times 4, that's 20. 23 minus 20 is equal to 3. Denominator stays the same. Forwards, backwards. Actually, I think it's probably a good idea when we're practicing to always verify the transformation we're doing by doing the other transformation as a verification tool. Why not? I think that's a good idea. 5 3/4. And you see the relationship. See what's happening. And one thing that's really easy to see is there's that 4. And there's the 4, there's the 4, there's the 4, there's the 4. That denominator really likes staying the same as we go through either of these processes. And that makes it a little easier to kind of not be distracted too much by that 4, by that denominator. It's a little easier to see what's happening with the numerator. Big times denominator plus numerator is the same as this. How many times does denominator fit into the numerator thing, and what was the remainder when we did that? It's really the same thing that we're doing forwards, backwards. The wording of describing it sounds like it's 2 different things, but it's not 2 different things. We're really doing the same thing, but we're doing it in 2 different directions. That's cool. I'm glad I took the time to do this verification. How about, I put another really small, simple looking one for my next example. And I'll tell you why. Because first I had a whole bunch of examples in all sorts of random order, and then I decided to reorder them so that I started with 2 as the numerator, the denominator. Then I did one with 3 as the denominator, then I did several with 4 as the denominator, and then 5, and then 6, etc. Let the denominators gradually become bigger so that the students can form confidence and realize that they really don't mind if the denominators get bigger. It doesn't stop them from being able to do the technique. 1 1/4. What if it's 1? What do I do when it's 1? No problem. Big number is 1 times denominator is a 4. 1 times 4 plus numerator, which was also a 1, over same denominator. 1 times 4 equals 4 plus 1 equals 5. Denominator still 4. 1 1/4 equals 5/4. It works. Okay, let's do another one right below it without erasing. But I'm switching away from these 4 denominators. 3 2/5. Big number times denominator. That's 3 times 5. plus numerator plus 2 over same denominator. Yeah, notice how that number, of course it did. Of course that's what happens. 3 times 5 is equal to 15 plus 2 is equal to 17. 17/5 is my answer. I have it. It is correct. It is good. It is fun. Let's do some more. I'm still sticking with 5 as the denominator for a few more examples. Look, Mocha's example has an 8 as the denominator. I have to go way down the page to get to my 8s. Okay, we had 3 2/5. How about 3 4/5? So what happens when all that changed is that the numerator got a little bit larger? Well, therefore, not very much changed. Big number times denominator, 3 times 5, plus numerator, plus 4, over same denominator, equals, hey, I can jump ahead and just do this right away if I want. 3 times 5 is 15, plus 4 is 19. 19/5, we have it. How about 6 1/5? I'm going to start playing around with another way of showing this to show it more quickly. Now, don't move to doing things too quickly, too soon. If this is helping you, do it. But I can also say, big number, that's the 6, times denominator, that's the 5. 6 times 5 is equal to 30, plus the numerator, that's a 1. 30 plus 1 is equal to 31. Denominator is the same. So I did this step, but I sort of did it out loud and in my head without writing it all down. And it still worked. I think I'm going to go back to showing this step though. I kind of like the way this step looks. There's something beautiful about the way the 5 is right above the 5. It's beautiful because it makes sense. It is interesting how things that make sense can be beautiful at times. Like my wife Bunny, who's upstairs. I frequently tell her when she's been speaking to me, you know, you make a lot of sense, Bunny. Yeah, she knows what it means. Okay. Still have one with 5 as a denominator, 4 3/5. Big number is the 4, times the denominator is the 5, plus the numerator is the 3, all over same denominator, equals 4 times 5 is equal to 20, plus 3 is equal to 23. 23/5, same denominator, it works. Do it backwards every now and then. Why not do it backwards? How many times does 5 fit into 23? 5 fits into 23 4 whole times. Plus 5 times 4 is equal to 20. 23 minus 20 is equal to 3. So the remainder and the numerator is 3. Denominator is the same. 4 3/5, 4 3/5, 23/5, 23/5. Gives me a lot of confidence. And it's another example of one of those great math things where when you're actually doing it in a position like in a test, if you were in a test, you kind of can use the other technique as a verification. You can do it and then check it and realize you're right. Before anyone shows up with the correction key, you can know you're correct. And it's nice to be in a test and actually know that you're doing something correctly. Math offers the opportunity to do that quite often, more often than a lot of other things that we study. It's one of the reasons I love math. Math is beautiful. Okay, I'm finished with all the ones that have 5 as the denominator. I'm going to move on to a few that have 6 as the denominator. And I'm also going to check the time and see how I'm doing. We'll do that little bit of math to figure out what fraction of the hour has been used and what fraction of the examples have been used. Really now we're getting to 44 minutes. We're almost at 45 minutes, which is 3/4 of the hour. What was my last example? Was the last one with a 5 as the denominator. There are 11 examples left. 10 examples, was because I had 40 examples, 10 examples would be expected to fill a quarter of the time, which is 15 minutes. This is so close. I don't know what was going through my head when I decided 20 examples of each would be good, but my instincts were good. Okay, how about 5 and 5, 6? Of course, there are going to be 42 examples in the end, thanks to Mocha. That genius dog, that beautiful assistant of a dog. Okay, 5 and 5, 6. Big number 5 times denominator 6. plus numerator 5 over denominator 6. 5 times 6 is 30. 30 plus 5 is 35. 6. We have our answer. Another one with a 6. Yes, I have one more with a 6. This one is 9 and 1/6. Let's ignore that. That's a smudge. Okay. 9 times 6 plus 1 over 6. 9 times 6 is equal to 54. Plus 1 is equal to 55. What a beautiful answer, 55/6. Who would have thought that something as awkward as 9 and a 6 would turn into something as beautiful as 55/6? I didn't plan it that way. Math is just beautiful by itself sometimes. Okay, let's do one with 7 as the denominator. We're getting close to the mocha examples. I need a sip of my fizzy water. Okay. 7. 5 and 3/7. Remember what we started with, 2.5. That was the very first one we did. So simple, these digits. 1 and a couple of 2s. Simple, simple, simple. Look at this. Look at this mess. We don't care that it's a mess. The fact that it's a mess is just making it more challenging, which is making it more fun. Okay. Big number 5 times denominator 7 plus numerator 3 over same denominator 7. 5 times 7 is equal to 35 plus 3 is equal to 38. 7's, same denominator. Yep, it's fun. Okay. Another one with 7. How about 4 and 2/7? Big number, 4 times denominator 7 plus numerator 2 over same denominator 7. 4 times 7 is equal to 28 plus 2 is equal to 37. Another beautiful answer. It's making me think about something. All of my examples have been really clean mixed numbers where the numerator is smaller than the denominator. But every now and then in math, especially when we're partway through a process, and we end up with a weird looking fraction where even though it's a mixed number, the numerator is still bigger than the denominator. What does that mean? Let's do a couple of examples, and now I'm just improvising, I'm not pulling examples off of this. Let's do a couple of examples to show what happens. I have a creative way of doing this, so making up another fraction that's different. I'll use 6 as a denominator. I only did that twice. And I'll use 7 as the big number. That's not matching any of my questions. So it's a mixed number, but the numerator is bigger than the denominator, so it's not a completely simplified mixed number. But can we still do the process? Yes. Yes, we can. So let's see what happens. 7 times 6 plus 10 over same denominator. 7 times 6 is equal to 42. Plus 10 is 52. So where it's going to look a little different is where when we do that verification, let us just use the regular method of converting the improper fraction to a mixed number. How many times does 6 fit into 52? It's not 7. It's 8. 6 times 8 is equal to 48, which is less than 52. 6 times 9 is equal to 54, which would be too big. So therefore, 6 times 8 is 48. 52 minus 48 is equal to 4. Denominator stays the same. This is kind of interesting. 8 and 4/6, which is not the same thing we started with, but the big number got one digit larger. Instead of 7, it's 8. The numerator is now smaller than the denominator. This still worked. Can we simplify this? Yes. We can also reduce this fraction. 4/6 is not in simplest terms. So I can reduce the 4/6. If I divide the 4 and the 6 by their common factor of 2, I get 2/3. So it turns out that 8 4/6 is actually the same number as 8 2/3. And it's the same number as 52/6. And it's even the same number as 7 10/6. Wow, there certainly are a lot of different ways that we can express the same number. This is fun, it's kind of interesting. I'm kind of going out there, I'm experimenting. I'm experimenting because experimenting makes me slow down, think about what's going on, and realizing that it's almost as if I'm trying to make myself feel confused, but I don't feel confused. I feel like it makes sense. So I like this. Let's go back to doing the question over again, except this time we're starting with 8 2/3 instead of 7 10/6. This is not in its simplest form because it had a numerator that was larger than the denominator, and the numerator and denominator were both even numbers, therefore it could have been reduced. But now we have it in a more simple form, and we'll just go backwards and do the conversion to improper fraction again. 8 times 3, that's my big number, times my denominator, plus 2, which is my numerator, over the same denominator. 8 times 3 is 24, plus 2 is 26. 26/3. That's what I can do here. I can multiply this by 1, but I'm multiplying it by this clever form of 1, 2 over 2, because that will give me a fraction where my denominator is a 6, and 26 times 2, yes, that happens to be 52. We're finding all sorts of different ways of expressing the same number. I hope that we all feel confident that there's nothing wrong with this, that all these different ways of expressing the same number happened because we started experimenting. And the experiments work because we know what we're doing, because we have processes that work. We know quite a few processes that work, and we're combining them here into a great, big, interesting example. But I'm going to go back to my list of examples that are straightforward. And I'm going to check my time. Doing pretty good for time. I'm finally at the examples that have 8 as the denominator, which means I'm at the examples that Mocha's example fits into. I'll do both of these first though, because they look a little simpler than Mocha's. 3 3/8. Big number times denominator, 3 times 8 is equal to 24, plus the numerator 3 equals 27. I'm jumping ahead. Same denominator. Okay, big times denominator, that's 3 times 8, plus the numerator, that's plus 3. I didn't forget anything. 3 times 8 is 24, plus 3 is 27. 27/8 is my answer. It worked. One more with an 8. 6 1/8. 6 times 8 plus 1 over 8. 6 times 8 is equal to 48, plus 1 is equal to 49 over 8. We did it. It worked. It's nice. Okay, let's do Mocha's. It would be great if I could get Mocha to do this herself, but I don't know how I would manage to do that. I know that one of the steps would involve somehow smearing dog treat all over the chalkboard wall so that she'd actually start noticing the chalkboard wall. It's kind of like the camera. I hold her right up to the camera so that you can say hi to her, and she just looks around as if she has no idea there's a camera there. But if I put dog treats on the camera, she'll notice it. Okay, 4 5/8. I need more chalk. Big number 4, I need this line longer, times denominator 8 plus numerator 5 over denominator 8 equals 4 times 8 equals 32 plus 5 is equal to 37. 37/8. Mocha made up a good example. It works just like all the others. She's a genius of a dog. Okay, I have some with some even bigger denominators. I have enough time left to do a few more. I have 5 more examples. I think I will finish with these 5 examples, and I'm just going to go through them quickly. I'm going to keep showing it this way though, because I like this way of showing it. 9 1/9. 9 times 9 plus 1 over 9 9 times 9 is equal to 81, plus 1 is equal to 82. That works. I'm a little off center now that I erased that other stuff. How about 3, look, I'm moving it over a bit. 3 and 8/9. Big number 3 times denominator 9 plus numerator 8 over denominator 9 equals 3 times 9 is equal to 27 plus 8 is equal to 35. 35/9 is my answer. It's a beautiful answer. Let's do, one with 10 as the denominator. Really, we could go on to some very large denominators and the technique's still going to work. 2 and 7/10. 2 times 10 plus 7 over 10. 2 times 10 is equal to 20 plus 7 is 27. 27/10, it worked. Here's one with a 12. 8 and 7/12. 8 times 12 plus 7 over 12. 8 times 12, that's getting pretty far down into the bottom corner of the multiplication table. 8 times 12 is 96. Plus 7 is 103. 12ths. Big numbers are not stopping me from being able to do this. How about 7 and 4/15. Now, I will stop for a second to point out that all along, we could have been using a calculator. I could have done things like, well, this 7 times 15, I could do that with a calculator. And if I needed to, I would get the calculator. But it is nice to exercise the brain muscles to try to do it without the calculator if you can. But what if we had such big numbers involved that we needed to use a calculator, that would get to, well, it would be harder to do it the way we've been doing it. You might have to do multiplications and maybe even additions off to the side somewhere. You'd still be able to do them with pencil and paper. So you don't really have to resort to a calculator, but you can. 7 times 15 happens to be 105. I'm jumping ahead though. I have to write my process. 7 times 15 plus 4. 7 times 15 equals 105. 7 times 10 is 70. 7 times 5 is 35. 70 plus 35, yeah, that's 105. Plus 4 is 109. 109/15. We can do it. We can do it. I'm going to erase because I'm going to do one more bonus question. A nice big one. Just to challenge myself. Just to make the point that there's nothing to be scared of. How about 36 and, let me make this longer, 42/57. Am I going to get the calculator? Yes, I am. Mainly because of time though, because can I multiply 36 by 57? Yes. On pencil and paper or on chalkboard and chalkboard wall? Yes, I can. So I could do this without a calculator, but I'm not going to prove it because this lesson is just about time for it to be over. So I'm doing, of course, the same process. 36 times 57, there, plus, too messy, okay, plus 42, I really had to make this line long this time, over same denominator, 57. 36 times 57 equals 2052, plus 42 equals 2094. I was able to do that. Calculator helped. Well, it made it faster. Made it faster, that's all. What about doing it backwards? 2094 57ths converted into a mixed number. How many times does 57 fit into 2094? Well, that might take a while. We already know what the answer is going to be. It's going to be 36, isn't it? But let's say I didn't know that. 57 times 22, 1254, way too small. 57 times 29, 1653, still too small. 57 times 33, 1881, I'm getting there. 57 times 35, 1995, really close. Yeah, I'm going to do 36. 57 times 36, 2052, and I won't be able to add another 57. It would go over 2094. So 36 is my big number. 2094 minus 2052 is 42. Is it? Yes, it is. I'm double checking. And then denominator stays the same. Okay, so I don't think that I'm going to ask students to do either of these very often, but I did want to make the point that I'll bet you that an awful lot of students would be able to do it. Because once you know the process, and you know the process works, it gives you confidence and it makes you not afraid of some big numbers. And with that, I am going to say goodbye from me and from my beautiful assistant Mocha, who is upstairs thinking about supper and dreaming up new math examples for you to practice with. Have a nice week. I will see you next time.